designing, manufacturing, installing, and maintaining the high-speed electronic computer, the largest and most complex computers ever built.
Hello, everyone. Welcome to another episode of Building Better Systems. This is a podcast where we get together with people at the forefront of firefighting and working on making systems better and building the tools and approaches that kind of help them get there. My name is Spat Morina.
And I'm Joey Dodds. Today we're joined by Tycho Andersen, and Tycho's an engineer at Cisco working on Linux kernel security and kernel stability. Tycho spends his days working to solve really complicated problems that are going on in the kernel that are causing both Cisco and other companies to feel pain and causing their container infrastructure to suffer. And Tycho basically works tirelessly to make as many of those problems as possible go away while also improving the Linux ecosystem for everyone. He holds degrees from University of Wisconsin-Madison and Iowa State University. And it sounds like he's been an open source contributor for quite a long time. So this is a really, I think, ideal job for Tycho. Thanks for joining us, Tycho.
Yeah, thanks for having me. I'm excited to be here.
Now that we've informed ourselves thoroughly about Tycho, I'm gonna kick us off with our usual question. Tycho, what's your approach to building better systems?
Well, unfortunately, I don't know that I have a very good one. I think I feel like some days my job is just professionally catching knives, and I have never had any formal training in knife catching. So, most of my advice probably today is informed by just a long time of building stuff and seeing what goes wrong. Sort of at the core, I would say write more tests is good, and that's basically the number one thing, I guess. Yeah.
So yeah, we brought you on today, Tycho, because this is a really interesting counterpoint to some of the perspectives that we've shared so far, which have all been about sort of the most principled possible approaches to making systems better. But in reality, most people maybe don't have the time or energy to always take the most principled approaches possible. And you have to settle for something that gets things working today, that gets things working tomorrow, that stops your machines from crashing. Could you tell us a bit about what this knife catching entails, what you do day to day?
Yeah, sure. Yeah. So my day to day, I work on this Linux platforms team at Cisco, and I've worked kind of in the container realm, both sort of on the kernel and the low level user space that calls into containers and container checkpoint restore and container stuff since about 2013. So what I do day to day for Cisco is I'm a stable kernel maintainer for their platforms, and then also I do some feature development in the kernel for containers, and then also just some thinking about security, although that's very hard. So that's what I do.
So what are the implications of kernel stability on basically like our day-to-day lives? Like if the kernel's crashing, for example, how bad is it?
I guess the question is, it depends on which kernel is crashing. So so I work at Cisco and we deploy a lot of Linux all over. So mostly we're at the, network architecture level, and all of our systems are, the name is escaping me right now, highly available. There we go. So they all have failover and stuff. So for the most part, if one kernel goes wrong, it's okay. It's when there's like an issue that affects a lot of them. A lot of people have Linux running in their pockets on Android. If that kernel starts crashing, you're totally screwed. So I think people care a lot about kernel stability and have started to care a lot about kernel stability, I would say, especially in the last 10 years as Linux has gotten more and more prevalent. And there's been a lot of work, when Linux was first a thing, in the 90s, this was kind of before my time, really. I really became a full-time Linux user in 2007. But I think there wasn't a lot of testing, and people kind of put patches in, and if it broke, you got an email, and that's how you knew it broke. So the rest of the world was your CI system, which is fine if you're kind of a hobbyist project in the 90s. But now it's a very professional project powering gazillions of dollars of revenue, and so I think the kernel community as a whole has really woken up in the last 10 years and tried to do a better job of testing and things.
It's super interesting. We hear this over and over again. It's something, you're building something, and it's a hobby. You're kind of being involved as a hobbyist, and then later on that code goes on to be almost very critical to a lot of things. And then somebody has to go back in and work with these systems that have been built with not necessarily thinking like, oh, this is going to be, as you said, gazillions of dollars or maybe even lives, depending on this running well. I'm curious if you have any kind of thoughts for people who are writing code kind of as a hobby that might later on be, become that kind of impactful. Well, you can't know that by definition, but let me step back and ask this question: What can people do when they're writing code that right now might not have have other people rely on it massively, but let me restart this question. If you're working on code as a hobby and not as a profession, what are some low-hanging fruits from your perspective that wouldn't necessarily make it kind of a professional commitment of time that you might be doing that make those systems better?
Yeah, it's a great question, and I actually have some experience with this. So my one of my open source projects that I really have loved working on for a long time is this window manager called Qtile, and it's just a window manager written in Python, and it turns out it will never be valuable to anyone. Nobody will ever pay anyone to work on a window manager because we already have too many, and just nobody cares about window managers except for the weirdos on the internet who care, of which I am one. And if you look through the commit history of that window manager, you can see, because I've been working on that project for almost 11 years now, and you can see early on my commit messages were short. They're kind of, not very good. And then basically right about the time that I started becoming a Linux kernel contributor, everything really snaps into like very professional commit messages and with links to various documentation, here's this weird place in the X11 spec where this thing happens. Or one of my favorite goofy you always hear about how the X11 API is terrible. One of my favorite goofy things is in XCB, there's a thing where it uses the space in memory before the pointer you pass in. So you have to allocate some memory before the pointer you pass in. And I just think that's crazy. But the commit message for that particular thing, when I fixed that bug, has a big, long write-up of why this is and all this stuff. And so I think, it seems sort of unnecessary at the very beginning, but when that code becomes important, you or someone like you will have to do, but probably you, if you care about the project and you enjoy it, will have to figure out, why did I do this? And if you go back to the commit logs and you see, initial commit or fix XYZ or whatever, and there's not a lot of reasoning about why a particular line of code exists, it can be hard to hard to figure out what's going on. So I guess the thing that I've done now since I started working on the kernel was, in all other projects that I do, I write good commit messages, even for repositories of like my dot files and stuff. You do a lot of spelunking when you enable some one-line change in your bash RC or your ZSH RC or whatever, and like that's valuable time that you will have wasted that if you don't record that information somewhere. And so the commit log is a great place to do that. So I think the most basic thing people can do on projects they're working on today that aren't necessarily a big deal is just practice good commit hygiene. Make sure everything would always bisect, even if maybe nobody will ever bisect it, but it's just a good habit. And the kernel, if you ever want to be a Linux kernel contributor, that they force you to do that. I mean, your patch just will not get accepted if it doesn't follow, these very strict rules, which is totally reasonable. But I think that's just a super basic thing that is very, very valuable.
This has really been a recurring theme with people that we've talked to, is that we can't just look at technology. We published episode 2, which was with MuseDev, and one of the things they said is we can do all we want on the technology side, and if people don't adopt, and if people don't actually think about how they're writing code and how they're putting code together, the technology can't help. And it sounds like the Linux community, and I don't know when this started, but it sounds like the Linux community is doing a really nice job of holding people to that standard of explaining themselves. But it also sounds like you've taken that professional learning that you did and found it even valuable to apply to your personal projects, which sounds like a great example of actually that being valuable, right? Sometimes we do things at work and we have to tick the box for work. Fine, I tick that box. They wanted me to do it. But sometimes things you do professionally are really there for a reason, and it sounds like this is one of them.
Yeah, absolutely. I think it's a super valuable thing, and I've become a lot more strict about it with other contributors in my open source projects, just because I think it's important now after watching the Linux people do it.
Now you're that guy.
Now I am absolutely that guy, and I am totally unapologetic about it. This is a super important thing. So
that's brilliant. It's an excellent point.
And it sounds like the bar for doing that, it sounds like, is like, am I gonna maybe work on this next year? And if the answer to that is yes, then go ahead and just take that extra minute to write a good commit message.
Yeah, I mean, I sort of think about it like, well, you try and eat healthy now, you try and exercise now, you try and save money for your future retirement or whatever. Like, you do all of these other things to take care of your future self. Like, here's one more way in which you can take care of your future self, because odds are it's going to be you. So, yeah, totally. I viewed exactly the same way.
But it sounds like it sounds like Linux is maybe in the situation where it went off to college in the early 90s and gained its freshman 15, and maybe tried a few experimental things, and things got a little wild, and maybe part of your job is dealing with that at this point.
Right. Yeah. I mean, so I think if you look at Linux commit messages, they have always been very good, even before things like Git existed. I think they were very good about that. Now, yeah, the thing that maybe wasn't so good and has gotten better, to your point, is the testing. Now there's a Linux Foundation staffer, Shua Khan, and her job is to maintain case self-test and make sure it gets run and that kind of stuff. Whereas I think she was hired in 2017. So like pretty new thing to have a Linux Foundation fellow who just focuses on testing. Like this is we've had other testing and infrastructure projects. XFS tests has been around for a long time because the file system people, need to make sure their stuff isn't broken, but that's not part of the kernel repository. There's no integrated CI, or at least there wasn't at the time when they started that project. There's like the Intel build bot basically just tries to build everything that gets sent to LKML. And I think a lot of build failures started getting caught that way, because it doesn't just build x86. It built, in spite of being run by Intel, it builds all the architectures. And so, your thing may compile on stuff that most people use, but like Extensa or whatever, might break that compile, and you'll get an email about that these days. Or, I think maybe the most important project is the syscaller project by some guys at Google. I think it's led by Dmitry Vukyov, and that's been a super valuable project, over the course of the last 5 or 8 years, however long it's been going. So the kernel community is growing up, but there was some work to lose the freshman 15, indeed.
But I mean, it sounds like even good commit messages in the 90s, I think, was probably it's kind of a big deal, right? People weren't doing much CI in the 90s. So you can certainly be forgiven for not having a CI build in the 90s, and that like maybe everybody that had to approve it would download the thing themselves and try to build it and sign off. And maybe sometimes they sort of skipped it because it looked good to them and they didn't have time.
Yep.
But it sounds like it sounds like they've been pretty close to as quick to adopt these good practices as anybody has, basically.
Yeah, I mean, certainly around commit messages, I've never seen a project that was anywhere as good as the Linux kernel. I mean, to the point where, like, if you watch some of these interviews that Linus does at various conferences, I mean, he's like, I almost don't care about the code change. He's like, the commit messages, the part people are going to inspect. And, I mean, the other thing about the kernel is, like, there are probably hundreds, maybe thousands of engineers who are going to look at all this stuff because there's a big team of guys. When I worked at Canonical, they had 25 kernel engineers who were backporting stuff across their kernels. I think Red Hat has an even bigger team. SUSE has a team. I work for a team at Cisco where I regularly spend time spelunking through the kernel logs, trying to find, information about backtraces and all kinds of stuff. So there's hundreds or thousands of engineers all over the world that are going to try and figure out, like, oh, I have this bug. Generally, when I'm looking at a kernel bug, it's in some subsystem that I don't really know that well. So I'm sort of, grasping at straws already. So an explanation of, like, a healthy explanation in the commit log is very, very helpful.
Hey, you touched on this a little bit, but when we were doing prep for this podcast, you were telling us a little bit about your job, and it sounded really cool. I mean, you said knife catching, but the way I saw it was basically you were called in to do some, firefighting. A firefighter meets Sherlock Holmes kind of stuff, as it relates to kind of kernel stuff. I wonder if you could like tell us a little bit about what that entails day to day and what that looks like.
Sure. Yeah. So we have, I think probably like any large organization, we have some levels of support, and when the customer hits a kernel bug, it goes to some frontline support engineer, and goes up various levels until finally, most of the time, by the time it gets to me, it's been touched by a bunch of people. So the system is not in its original state. Often we have a backtrace. In fact, I enabled the use of a subsystem called pstore in the kernel, where we actually there's a small writable section in the ACPI tables, and now when one of our devices core dumps, we write this core dump stack trace the kernel panics. We write the kernel panic stack trace into the ACPI tables because often systemd will rotate away the logs before I even get it. And so the only place that we get this stack trace is from this like little writable section in the ACPI table. So often what I start with is an explanation of, here's a kernel stack trace, please fix this bug. And sometimes it will come accompanied with an explanation of, oh, we were doing this at the time. But usually it's like a user who's like, oh, I clicked on this JavaScript icon in the app. And that's, not really connected to what happened, on the back end when the kernel crashed. So, the first thing to do is, Google bits of the stack trace, and there's like, heuristics about how you can splice bits just to see if anybody else has seen it. Are there any other bug reports from this? A lot of times there's, the kernel bug tracker, but that's not so good. LKML will have some reports. So there's various places. One of my favorite bugs, probably my all-time favorite bug that I fixed while working at Cisco, was a bug in the TTY subsystem, which is like the subsystem that does all kind of the low-level text input and output when you're interacting with it, like over a serial console or something. And about, I think it was maybe 15 or even 20 years ago at this point, there was a guy named Alan Cox who worked for Red Hat, and he was the maintainer of the TTY subsystem, and he got into a fight with Linus about something. Linus didn't like the way he had handled something, and Alan Cox said, fix it yourself. I'm not dealing with this anymore. And the TTY system has not seen a lot of love. I think Greg Crow-Hartman is the maintainer now, and he just is so swamped. He doesn't have enough time to really sit down and, I mean, he'll fix bugs if people report them, but there's no active development going on. So anyway, I get this bug about this. I get this kernel stack trace, and I'm looking at it, and it's clearly a race condition, and I'm trying to think like, well, how would this happen? And it turns out basically that there was a critical section that was just protected by two different locks. So one function used lock X, different function used lock Y. They both look reasonable until you actually look at, well, this is lock X and this is lock Y. And so it turns out the race condition is pretty easy if you're using two different locks. So anyway, the result of this was, it turns out that Alan Cox had been right in the middle of a refactoring when he got annoyed with Linus and quit. And probably this is like a thing that would have gotten fixed if he hadn't gotten annoyed and stayed working on it, because he was in the middle of shifting to this new locking scheme. So anyway, the TTY subsystem has these two different locking schemes, basically because of this sort of people issue. So anyway, all this is to say, you can figure this out going back to, I figured this all out from the commit logs and looking at mailing list, postings and timings. But this is like sort of the spelunking that you do. Like you guys were saying, Sherlock Holmes. Sherlock Holmes was really smart. I don't know that I'm a Sherlock Holmes, but you spend a lot of time, more so than writing code, even just reading commit logs and doing this spelunking with stack traces and that kind of stuff, more than anything. So I don't know. I guess that's my answer. Is that a good?
Yeah.
Is that?
Oh,
I don't know.
it's fantastic. It's super interesting to see, not only to fix something, but also to kind of dive into like, how did it come to be from this essentially open historical kind of catalog of everything that happened, both as commit messages, but also just socially what happened.
Right.
We talked about commit messages. The Linux community is able to keep things relatively bug-free, and now with more and more kind of it being a critical part of a lot of things.
Well, it's good enough that my phone doesn't usually turn off in the middle of the day, right? Which is really good considering how much work is going on.
Exactly.
There.
And it's still kind of a community process, an open community process, at least the way I understand it naively. I'm wondering what does that process look like today? And, if there's other people working on things that are relatively critical, what can they steal from that whole thing, especially if they want to integrate a community in the process?
Yeah. I mean, I think the vision of the Linux kernel as a community process is totally correct. Now, it's not a community of hobbyists sitting in their basements. I get paid full time to work on Linux. Of various forms, whether it's user space or the kernel. But I get paid. And for example, this patch series that I'm working on now, we have people from Google, we have people from Red Hat, we have people from Canonical, all making the argument that, hey, this should go into the Linux kernel. And usually, especially, so the thing that I'm working on now is it's basically it's a container feature where you can UID shift file systems is what it is. So it's honestly a core piece of the container infrastructure that hasn't been implemented before, and it's kind of crazy that it hasn't, or it's been implemented but nothing's been merged. But it's a fairly big patch series, and I'm only small 2 patches part of it. But it's such a big series that you need collaboration from a lot of people, because if one person sends this big, huge patch series and says, hey, I want to do this crazy thing, everyone else is going to go, no, just figure out a different way. Where we have collaboration from all these different companies, and we all have said, yes, we want this, and here's the way we're going to use it. And all of our use cases are different. And there's been versions of this, that have surfaced before that wouldn't have satisfied Cisco's use cases. And so we've had to go to conferences or, since coronavirus, do the online thing and sort of, sway people. We get in these conferences and we sit in the rooms and we say, well, here's our use case. your solution doesn't work, but if you modify it like this, then we're willing to lend engineering time in the form of my time to help you. And so that it really is sort of designed by committee for all of the good things and all of the faults as well. And there's a thing I mentioned before is the ABI is stable, and so it can never be broken. So once an API goes in, it will always be there. So it really pays to think about the API before you put it in.
Maybe the fact that it's so permanent kind of makes that level of thinking about it and being deliberate almost a must.
Yeah, which is maybe one of the reasons this has not existed for the last however long, even though it seems like an obvious feature, but it just incarnations before this current one that we started working on maybe in February just wouldn't have solved all the problems that we needed it to solve. So the community is pretty conservative about adding new APIs, which can be annoying because we've been feeling this pain for the last 5 years, and Ubuntu has one set of out of tree patches in their kernel, and other people solve this other ways. But now that we've all been kind of doing this in the painful way for a while, we have a little bit better insight about what we actually need in order to accomplish our goals. So, the fact that we can design one API that does lots of things for lots of people probably means that it's a fairly reasonable primitive instead of just a one very narrow use case that one person had.
I think it's really amazing. The myth you dispelled earlier of it's all hobbyists hacking in their basements. I think a lot of people maybe still hold that about open source, but it's almost more amazing when you think of the fact that not only are you mentioned some, in some sense, downsides for the company, right? Like I'm sure a company that Cisco would maybe rather not have to argue its case to other companies, but it's also a clear indication of the value that Linux is bringing to all of these companies that you stick with it. So for every bit of design by committee, obviously you feel that you're getting that much effort from every other company that's playing part in this game, and that everybody's kind of winning together, which is a really inspiring story, I think.
Yeah, I mean, it's much easier for me to spend a few conference evenings or whatever arguing with people about how an API design should look than implementing, the whole thing from scratch myself or with a small team or whatever. So there absolutely is a lot of value created in just having this thing that for the most part you can grab off the shelf. And I mean, we have to build all our own kernels, and we have a lot of infrastructure to build all our own packages and all this stuff. So it's not free, but it is. I think basically, as long as Linux is around, you're going to have to pay guys like me to just babysit it. But paying guys like me to babysit Linux is much cheaper than paying guys like me to write your own operating system from scratch. So,
yeah, well, in the work you do, Cisco could arguably fund its own kernel development if it needed to, and it can fund you to take care of things. But there's tons of companies that start up depending on Linux that could never, that for years couldn't afford a single kernel developer, right? And they all get to benefit as well.
Yeah, absolutely, for
it's
sure.
really wonderful.
Yeah, it's a weird. My cynical self is like, "What's the catch?" But in a way, it's all whatever rising sea, something, whatever the idiom is, something about ships. But it seems like everybody benefits from this in a way. And the downside is that you get to argue a lot and get to work with people really close to convince that it's one way or the other.
Yeah, and I mean, I think there's a fair amount of people, like when I first got a job working on Linux, my dad was like, so what do you like, what's the value prop? Like, why are they paying you? And I think it has taken maybe some companies longer to understand the value prop. Maybe Cisco is even one of those that maybe they should start participating and giving back. But people are figuring that out, and they're getting that message. So it's really nice, and it's fun because I'm doing the same thing I would be doing anyway. I've been a Linux desktop user for a long time, and it's painful. So at least now I can get paid to fix all that stuff.
I think a lot. I wish a lot more communities, including I guess the formal methods community, which is the one we play the heaviest part in, could learn from this a bit. And I think at Galwa we've started seeing this even internally. We've historically had a lot of siloed projects, and all of a sudden things are starting to meet in the middle, and there's a lot of friction there, right? As you mentioned, sometimes you're doing design by committee when you just want to implement the thing. But and you go through that pain, but then like the next day you see like, oh, I wanted this new feature. I can't afford it on my project, but great news, somebody else was doing it anyways, and I just got that, right? Like I didn't have to lift a finger. And I would love to see that in that community across companies as well. Like I think it would be like, it's a real win for a lot of communities, and Linux feels like the standout example.
So I want to change kind of gears a little bit. You mentioned APIs earlier, and I suspect that if I'm an engineer developing conventional applications that run on software systems, that word means something very different than what it means to you developing essentially on, or like hacking on the Linux kernel. I'm curious what those differences are, and then I'm curious if there is something for those two groups to learn from each other.
Yeah, fair question. Um, I think in some sense it's the same thing. It just looks different. So the API for like a Linux system call, for example, is you put some, depending on your architecture, you either put some information in registers and then some more information on the stack, or it's all on the stack or whatever. And then you issue a int 80 or whatever, or the syscall instruction or whatever your thing is to trap into the kernel, and the kernel reads off the information out of the registers, out of your stack or your heap or wherever, and then proceeds to operate on it. So that looks a lot different from I'm going to HTTP post this JSON blob to this endpoint, and then something happens, and then I get this result back. But a lot of the problems are kind of the same. So for a while, people were adding system calls to do things, and so that the mechanism I just described was the way that you added new functionality to Linux kernel. Then for a while, I think for whatever reason, it became very out of vogue or impolite to add new syscalls. And so people put a lot of information and various things in /proc. So for example, if you're turning on a Linux security module, an LSM like SE Linux or AppArmor or something like that, you actually do that by writing to a proc file. There's no system call for that. Or if you're configuring a user namespace, if you're trying to set up the ID mappings, you do that by writing to some file in /proc. So those are API calls, but they're really writes to a file, and they're not system calls. And then more recently, we've kind of gone back to, in Linux, the system call model for a variety of reasons that are, I don't know, more just specific to Linux than anything else. But the most recent syscall rash of syscalls that people have been implementing are there's a document, I think maybe 2 years ago, that was put into the kernel documentation tree about what they call extensible argument syscalls. And it's a way to design system calls so that you add elements to the end of the structure, and it talks about how things should behave and under various conditions. If your kernel is newer, if your user space is newer, blah, blah, blah. But the core of that really is versioning. The kernel, as the kernel adds new functionality, it basically wants to version the API, and this extensible argument mechanism is a sort of a fancy way for us to do API versioning with just very basic memory passing and stuff. But the key takeaway, I guess, is if you have an API, you should have a way to version it. And I think people who are doing JSON APIs and HTTP can also take that away too. If you have a config file, just stick a version 1 at the top. Just some way for you to add or grow or change the semantics of that without totally breaking all of your users. I guess that's kind of the number one takeaway from Linux kernel API.
And it's best to do that from the start. Like even when
Yes.
you're doing your first, point oh one version, if you put the version there and require it, you're going to be happy later on. It sounds like.
Yes. And users of Qtile who are listening to this will be very angry with me because we often break the API in Qtile. Sorry.
do as I say, not as I do, kind of thing.
Yeah.
Cool. Thank you for that. Another thing that's on my mind is when we talked about. So I want to go back to kernel CI and kind of finding things that are wrong and finding bugs in kind of new code. I think my understanding is that there's some tools and approaches there that have kind of produced a lot of really good results. I'm curious what those are.
Yeah. So for CI, I mean, the story is really sort of K self-tests, XFS tests, to a certain extent, tools like FIO for performance measuring and block devices and stuff, and file systems. Those are good tools for catching regressions, and for testing new implementations of a file system or whatever, for performance aspects. But there's also, any talk about kernel testing would be remiss if it did not mention, I think, the work that's been going on in Google and Syzkaller. That's Syzkaller, which is it's kind of a pretty basic fuzzer for the kernel. It's grown a lot now and it's a lot more advanced. There's a whole DSL, domain specific language for designing like interleaving system calls and stuff, so you can get the kernel into particular states. But Syzkaller has found lots of bugs. It's found lots of bugs in code I've written. It's found lots of bugs in code other people have written. It's found lots of very security critical information leaks and stuff, just behavioral bugs, kind of everything. And they, it's the guy who leads the project is Dmitry Vukiov at Google, and he's done an amazing amount of work that's very good, and they found a lot of stuff. And in particular, they have a bug tracker that's open, so if you want to fix sort of some are basic bugs in the Linux kernel, that's a great place to start. But it's quite an amazing tool, and it is really, I think, has made kernel developers pay more attention to that kind of thing, to the just validating inputs, making sure that we're not in these sort of very basic copy from user, copy to user kind of length errors, that kind of thing, because they know they'll get a million reports from Syzkaller if they screw that up. And, people kind of joke about how annoying it is that it's sending all these emails, but all these emails are real bugs. And on most emails, it doesn't always have a reproducer for how it got there. But on most emails, there's a C program attached that if you run this C program, it will cause a kernel splat. So it's very hard to ignore.
Yeah, I'm curious what your thoughts are on what makes it such a successful tool. It sounds like, is it just because it's there at the end of the day?
I think so. I mean, I'm sure part of it is just that Google has put a lot of resources in terms of just compute power behind running lots of instances to find all these bugs. But they also hired the team to build the tool, and I think there are other companies now contributing to it too. But I think it's primarily driven by Google. I mean, I think just being there, and they're doing lots of interesting things too. Like they're not just fuzzing at the syscall level anymore. They're doing like USB device drivers. So what happens if I write a bunch of random junk to this USB device? Can I make it crash in a certain way? And these are like real bugs that people could exploit. If I can get like root access on your machine just by plugging in a bad USB stick, that might be a problem. So they've been doing a lot of, I think, very good work. So.
It also sounds like the fact that it provides an actual runnable program that then you can play with as you try to fix something potentially might be, or at least to me naively sounds like it might be a factor of helping you to engage with it.
For sure, at least from my perspective, when it finds bugs in my code, often it will send this C reproducer and say, run this, and that makes it very easy to, just look at the race or whatever. So it will sometimes take a little while because it'll have two threads and they're trying to do something very fast, but um, it will eventually reproduce, and that is, I would say, very, very useful.
And that makes you think about what user experience UX means for kind of static analysis tools, or just basically tools like this that are for developers, because that sounds to me like a really good kind of UX choice.
Yeah, if you think about any program that has an API, if you send somebody like here, like if you have a JSON API, if you're fuzzing your JSON API, it could generate a curl, blob that, hey, when I paste this curl blob with this curl command to your thing, bad things happen or whatever. But it's basically, here's an input that makes your program crash. That program is, this your kernel or whatever, but it's a similar thing. Yeah, it's a great UX.
Very cool.
Do you think there's work to be done still in the automated testing world? Like, is there a lot that you mentioned? It's a pretty straightforward fuzzer. I'm going to say, is there if you're in the automated testing world, is there a call to action where you could maybe crash the kernel in some high impact way and find a really impactful bug if you apply your tools in this space?
Yeah, so I think there's probably a couple of different ways in which there could be more automated testing or better automated testing. Maybe the first is on the, it's a fuzzer, and they have a domain specific language so they can explore the call graph a little bit deeper. But I think it's still it's a pretty shallow exploration of things. Like, for example, in order to set up a container, you have to do a series of syscalls, write all the right information to these proc files, and do a series of more syscalls. And syscaller is just not going to be able to explore that very well. So that's one of those things where, in order to there's how many container runtimes, and all of them implement some version of this series of steps. And surely some of them must get it wrong, and we don't have any real way to check that. But also, just on the kernel side, right now there's KMSAN, which is the kernel memory sanitizer, KTSAN, kernel thread sanitizer. So there's a lot of these error checking things, is the kernel in a bad state on the kernel side? And implementing more of those types of ideas, syscaller turns all of those things on. And if any of one of them triggers a bug, then they send you their reproducer and blah, blah, blah. So if you can upstream something like that into the Linux kernel, you don't actually have to write any more test cases, because syscaller's all running them already. You just email Dmitry Vukyav, or probably you don't have to email him. He's picking up on this stuff. But as soon as it lands upstream, he'll just turn it equals Y in his kernel config, and then whatever bugs your thing can catch will then all of a sudden be caught by all of the syscaller instances that everyone's running. So I think there are a few different avenues. If you can all of a sudden, we need to do this runtime instrumentation, but we can catch this class of bugs that nobody knows about right now, that's a useful thing too. And there's already a whole bunch of dynamic testing going on. So if you just implement that thing, that is very useful.
So if you are a automated testing researcher, I encourage you not to do that because I want to do it. So please don't take those projects and run with them, because I'm honestly pretty excited about the idea of doing that. And it sounds like a great place to apply these techniques.
Well, we can take a page from the Linux community and maybe do it together.
Well, the second, the idea of broadening the impact of the current tools is whenever possible, is definitely the right way to do things rather than building new tools. It makes adoption easier. Of course, people are already very comfortable, it sounds like, receiving those emails. And so, it sounds like anybody going after these problems would certainly be best served by understanding the syscaller work and whether it could be extended in the direction that they're taking it, rather than trying to build their own thing that will result in one more form of slightly annoying but respected email from kernel developers, basically.
Yeah, totally.
Well, this was a fantastic conversation. Thank you very much for joining us and for chatting with us about all this. I had no idea what really goes on these days in kind of kernel space. So this is awesome.
Yeah, thanks. Thank you guys for having me.
Absolutely, yeah. Well, this has been another episode of Building Better Systems with Tycho Andersen. We'll see you everybody next time.